Alright, so this is where we left off. Our second boundary condition, ladies and gentlemen. Right? So we developed the left-hand side, developed the left-hand side of this equation, and now we gotta focus on the right-hand side. Let's see if we can develop the right-hand side of this equation. Okay, this right here is the left-hand side. This right here is the left-hand side of the boundary condition, but now we gotta develop the right-hand side. So the right-hand side, let's switch colors. H times the heat transfer coefficient times the temperature at the outer radius minus the temperature of the air. Okay, and that's going to be equal to the heat transfer coefficient times the expression for the temperature itself. So the expression for the temperature, this one, that's just going to be negative A over K. Let's switch colors. Negative A over K times what was that? Times what was that? Okay, it's gonna be R squared. I'm just gonna skip some steps, if that's okay. I'm gonna skip some steps, and hopefully if I don't make a mistake, this is what you're gonna get. 7 over 60. 7 over 60 times R squared. Okay, 7 over 60 times R squared plus C2. Alright, close that parentheses, minus T infinity. Hoping this one's good. Okay, and now we can just take left hand side and equate that to the right hand side. So what you're gonna get is now we're just cranking the algebra. Now we are just cranking the algebra. So my left hand side 2 over 15 times AR, okay, is equal to all this crap. H negative A over K times 7 over 60 R squared plus C2 minus T infinity. Okay, crank the algebra and C2, crank the algebra and C2 is our unknown. So I'll just do some algebraic steps, just for the fun of it. Okay, I'm gonna divide both sides by h. That's how I'm gonna start off. I'm gonna divide both sides by h first. Okay, boom boom. And then I'm gonna add T infinity to both sides. Then I'm gonna add T infinity to both sides. You're gonna get 2 over 15 AR H plus T infinity. And all of that is gonna equal negative A over K 760 R squared. 760 R squared. Okay, just making sure I'm not missing any parentheses, right? Plus C2. And voila, C2 is just gonna be equal to our final algebraic step. Gonna be equal to 2 over 15 AR divided by the heat transfer coefficient. And by the heat transfer coefficient. Let me just pause for a second and see if I haven't. Let's see if hopefully I haven't made any mistake. But again, I'm just human, right? Now we're good. Now we're good, boys. Win. Ladies and gentlemen, win. We're in for business. Plus A over K. We can just if my OCD is kicking in, I'm just gonna write the numerals. I'm just gonna write the numbers first. Good. So I have my C2 now. And keep in mind my C1 was equal to 0. Right? C1 was equal to 0. So I've evaluated both constants of integration. So let me just grab this once again. So we can rewrite everything. And what I'm hoping is that most professors would be kind enough at this point. Most professors would be kind enough and would be satisfied with what you've done here in an exam condition. But, well, some won't be, and that's okay. That's okay. That's not going to stop us, right? So yeah, the temperature profile. The temperature profile becomes all this negative A over K R squared over 6 minus R to the power 4 over 20R squared, and copy all of this crap. Oops, nope, we're still learning technology. I think I got it. Guys. I think I got it. All right. Well. Let's see. Nice. Ah, I'm missing the 2. I am missing a 2, but hey, that's not gonna stop us. Okay. So this right here is my temperature profile. I have my temperature profile in the sphere. Very good. What next? Now I'm just gonna give you guys a overview, a brief overview of what you guys can do from here. You can find maximum temperature. All right, you're looking for maximum temperature. Okay, you can find the rate of heat transfer. Okay, but how? How are you gonna find the maximum temperature? Just gonna take the derivative of your temperature profile and set that equal to 0. Okay, and then solve for r. Solve for the value of r that gives you the first derivative as 0. And I'm not sure yet. In this case, it's gonna be a maximum temperature because like we're having heat generation. In this case, we're gonna have a maximum temperature, I believe. So yeah, just some basic calculus. And what about this one? What about this one? So, and that's just, if you guys remember, that is going to be equal to, you can do that by, if you like the rate at which we're removing heat, you can start off by calculating the value. You can start off by calculating the value of negative k dt dr at r equals r. Okay, and that's going to give you the flux. That's going to give you the flux at the surface. Once we have the flux at the surface, you just have to multiply by area. Okay, because flux is going to be heat over area. So q dot is just going to be the area of the sphere, which is going to be 4 pi r squared times this thing. Okay, the flux evaluated at the surface. All right, so I hope this was helpful. All right, this is just gonna be an exercise for you guys, because the next step, once again, the point I'm trying to emphasize here is that once you have the temperature profile, everything else, from there on, everything else is just calculus. All right, now you just have to use some calculus. So yeah, guys, thanks for sticking around till the end. All right, I hope this was helpful, and yeah, thank you guys.